Welcome back to the deep dive. When you think about it, everything digital, from simple apps to complex operating systems, it's all built on instructions. Today, we're going to dig into, well, basically the original blueprint for telling computers what to do, procedural programming.
That's right.
And a programming language, really, it's just a set of rules, symbols, that lets us humans write code, instructions, stuff the computer gets perfectly, even if we only mostly get it.
Exactly. And consistency is huge here. You hear a lot about newer paradigms, right? Object-oriented, event-driven, all that web stuff. But procedural, it's not just history, it's fundamental. So much is still built on it. It was a big step up from assembly language, made managing complexity way easier.
Okay, so our mission then is to really get the DNA of this approach. Procedural programming.
Yeah.
It's all about procedures. You might call them functions, subroutines. The focus is really on how you solve the problem, breaking it down, step-by-step actions, a clear sequence.
Think of it like a super detailed flowchart, basically. And to see why it works or, where its limits are, we need to look at its anatomy, how procedural code is structured. Because, you can't just write one massive block of code for a big task. You need modularity. And that starts small.
Right, with the smallest piece. The statement, we hear that word all the time, but what does it really mean here?
Okay, so a statement. It's the smallest thing that actually does something.
Yeah.
A single instruction, a single command the computer executes. And this is critical because the whole procedural idea relies on running these statements one after the other. Sequentially, that gives you predictability.
Determinism.
Exactly. Our source material gives some good examples, like if you're changing a value, that's an assignment statement, x equals 10, maybe.
Yeah.
If you need to show a result, output statement, something like print, hello. And really important for breaking things up. If a specific task calculates something, you use a return statement, like return value. The whole program is just, a long sequence of these little actions.
Okay, and once you have a bunch of these statements doing related things, you need to group them, visually, logically. That's the block, isn't it?
Precisely. A block is just a way to group related statements.
Right.
It helps structure the code, makes it readable, and, importantly, it controls the scope of variables. You see it with curly braces in C-like languages or indentation in Python. It defines, the body of a loop or what happens inside an if or everything inside a procedure.
It feels like it was designed to combat that old spaghetti code problem where execution just jumped all over the place. Blocks bring discipline.
That's exactly the historical context, yeah. And once you can group statements into blocks, the obvious next step for efficiency and scaling is making those blocks reusable, which brings us to the procedure.
The star of the show for this paradigm.
Yeah.
So a procedure, it's a named chunk of code, a block of statements you can use again and again, performs a specific job. This is how you get modularity, right? Breaking the big problem down into callable bits. Instead of writing the calculate tax logic everywhere, you just call calculate tax.
Yeah, huge time saver. Code reuse is massive. But there's a kind of interesting nuance here, especially if you look back at older languages like Fortran or Pascal.
You mean the difference between a procedure and, say, a function?
Exactly. We often use the terms interchangeably now, but historically, a procedure didn't necessarily have to return a value. Its job was just to do something, write to a file, update a global variable, whatever. A function or subroutine, though, was typically designed specifically to compute and return a single value. That difference mattered more back then for managing memory and keeping the program flow clear.
Interesting distinction.
Yeah, but the main point for both is that they let you structure your code, make it modular.
It really hammers home that this paradigm is about action. Call the procedure, the steps run in order. Okay, so we have our organized procedures, our blocks. But code can't just run straight down forever. We need ways to direct traffic, right? Control structures.
Oh yeah, absolutely essential. Control structures are, they're the brains of the operation. They decide where the program goes next. You can't solve real problems without them. There are basically three main types.
And the first one, sequence, is just the default, right? The natural flow.
It is. Top to bottom, line 1, then line 2, then line 3.
Like that example. Declare x, add 5 to x, then print x. The result is guaranteed because it happens in that exact order.
Simple, predictable. Makes debugging easier because you can often just trace it line by line.
But simple only gets you so far. Programs need to react, make choices. That's the conditional structure.
Exactly. This is how the program adapts. Based on some condition, it chooses which path to take. We use if-else statements, maybe switch case in some languages. Think about that login example. If age 18.allows s, if not else, shower message. The program evaluates the age, then branches to run only the code that applies. It adds flexibility.
Makes sense. So if conditional is about choosing one path, the last type, iterative, is about doing things repeatedly. Efficiency through repetition.
You got it. Iterative structures are loops. Your for loops, your while loops, they tell the computer, run this block of code over and over until this condition isn't true anymore.
Yeah.
It's super important for handling lots of data, like that inventory example. While stock available dot, process order, update inventory. You don't write process order 1,000 times, you just loop.
Saves a ton of code.
It does. But loops are also where you can get into trouble in procedural code. If you forget to update the condition inside the loop, maybe you forget that update inventory step in the example, you get an infinite loop.
Ah, the classic bug. The program just gets stuck repeating forever.
Yeah, a common issue tied to how procedural code often manages state.
That's a good point. Okay, so we've got the structure,
Yeah.
statements, blocks, procedures, and the navigation dot sequence, conditional, iterative. Now let's shift gears a bit. Why use this paradigm, especially today? What are the trade-offs?
Right. Well, it definitely still has its place, and that's because of some core strengths. First, it's often really easy to grasp, especially for simpler tasks. The flow is linear, predictable, follows that sequence we talked about.
Easy to learn, easy to trace.
Yep. And second, something that was crucial historically and still matters in areas like systems programming, it can be very efficient with memory because you're often dealing with more direct control and maybe global data. There's potentially less overhead than some other paradigms. That's why things like operating system kernels often use C, a procedural language.
Okay. Efficiency. And we already mentioned reusability through procedures, which helps with maintenance on smaller projects. Fix a bug in the procedure, it's fixed everywhere, it's called.
True for small to medium stuff.
Yeah.
But,
Mhm.
and this is the big but, when those applications start getting really big and complex, those procedural strengths can flip and become major weaknesses.
Right, the complexity factor. Let's unpack that, especially how it relates to data. You mentioned global data earlier.
Yeah, that's a key issue. In classic procedural programming, data often lives in this sort of central global space. Any procedure can potentially read it, and any procedure could potentially change it. There's not much protection. So one procedure over here might accidentally mess up data that a completely different procedure over there relies on. These are called side effects, and they could be incredibly hard to track down in large systems.
So the data is kind of exposed, vulnerable, and that ties into maintenance, right? If data is shared everywhere.
Exactly. It creates high coupling. The procedures become tightly linked, dependent on the exact structure of that shared data. So if you need to change that data structure, maybe add a field, you might have to go find and update, 50 different procedures that touch it. It gets risky and time-consuming fast.
A ripple effect of changes. Sounds brittle.
Can be, yeah. Very brittle at scale.
Mm-hmm.
Which also leads to other problems our sources mention, like code duplication. Sometimes it's just easier to copy-paste code than try to figure out if a suitable procedure already exists and how changing it might break something else.
Avoids the coupling problem by just making another copy. Yikes.
Not ideal. And maybe the biggest limitation, the whole top-down, step-by-step model just isn't a great fit for a lot of modern software.
Like what kind of software?
Think about graphical user interfaces or web servers. These are event-driven. Things happen unpredictably, mouse clicks, network requests, user input arriving at any time, maybe even concurrently. Procedural programming's linear, predefined flow struggles with that. It expects to be in control, following its sequence. It's not built for reacting to multiple asynchronous external events easily.
Okay, so wrapping this up, procedural programming. It's defined by this structured step-by-step approach. Statements make blocks, blocks make procedures or functions for reuse. And it's all directed by sequence, conditional choices, and iterative loops.
Right. And for the right size and type of problem, that gives you code that's modular, pretty efficient, and relatively easy to follow and debug. But the core weakness, especially as things scale, is often how it handles data that's shared global state concept. Leads to tight coupling, maintenance headaches, and difficulty with event-driven systems. Understanding that weakness is crucial.
Yeah, and understanding that weakness perfectly sets the stage for our next deep dive. We'll be looking at the paradigm design specifically to tackle that data exposure problem, object-oriented programming, OOP.
It's a fundamental shift. If procedural code treats data like it's public property, open for any procedure to change. Think about this. How would you have to change the whole concept? How would you structure things differently to protect the data, to tie the data more closely to the code that's meant to operate on it? Reducing that coupling, reducing that maintenance risk, that required a completely different way of thinking about organizing programs, something to mull over.
Definitely something to think about. We'll explore that next time. Catch you on the next deep dive.